Okay, let us continue talking about fault detection observers. And in this second part, we are introducing threshold computation and detectability analysis. And finally, an example. So in the previous lecture, we have seen that we can compute the residual dynamics in healthy conditions as this equation. Where remember, delta is called the total uncertainty, and it is depending on the uncertainty on the process eta, the one on the measurement xi, but also on the actual value of the measurement y and the input u. So this is something that is varying over time and depends on the trajectory of the system. So in short, we can call this equation via this symbol. So say that this is a mapping sigma of the previous value of the residual and the previous value of the uncertainty delta. So delta in full is written like this. So it is equal to the nominal dynamics applied to y minus the uncertainty and u, y here and u, plus the process uncertainty plus the measurement uncertainty at time k plus 1. Okay, so now that we have here, all the problem boils down to finding an upper bound on this. And this will going to be our threshold. So remember, we are working under the null hypothesis. So the fault is not present here. So one thing that we will need later, if we want to prove some theorems, is the triangular inequality. So in the direct version, the triangular inequality is telling us that if you have a triangle and you have a side that you call A and one that you call B, and the side C that is equal to A plus B, when A and B are vectors, when in order for the triangle to close and not to stay open, you need that the length of the side C should be less or equal than the sum of the length A and the sum of the length B. But if you take this and you turn it around, you can also get these other two versions, which are the reversed versions. So the norm of A plus B is bigger or equal than the norm of B minus the norm of A, or the other combination, the norm of A minus the norm of B. So in general, these are norms when you're talking about vectors, but if you are talking about scalars, these are absolute values, and we're going to use absolute values later. So indeed, now we use this, the triangular inequality, together with a theorem that is called the comparison lemma by Grujic and Chiliak, to bound the absolute value of the residual. So we start from the equation that we remember is this one. R at time k plus 1 is equal to lambda R at time k plus total uncertainty delta. So now, in order to proceed and use the triangular inequality with absolute values, we need to consider one component at a time. So we can write that the I component at time k plus 1, its absolute value is less or equal than what? Lambda I small that multiplies the absolute value of R at time k, still the component I, plus the absolute value of the uncertainty component I at time k. So what we have written here is assuming that lambda is equal to a diagonal matrix. So lambda is a diagonal matrix with the individual lambda I eigenvalues on that. And so in general, they can also be negative. But let us assume for now, to simplify our life, that they are positive. So lambda I belongs to the interval 0 to 1. So they are stable, they are positive. So you can also consider a case where they are negative. It's not changing so much. You need to use the another inequality that bounds the norm of a product. But let's keep it simple now. We can also consider actually the case where they are negative. It's not changing so much. So we need just to put an absolute value as well here. So now we can replace this by an upper bound, which we assumed we know. At least I told you that we know. I will show later how we compute it. But for now, let's go on. And we write it like this. So we introduce now the upper bound on the component I of the total uncertainty delta. So basically, we took this and we further upper bounded it by this expression, where now we have delta over bar in place of this one. So this is such that is always bigger or equal than the absolute value of that component of delta. So by definition, we have this term. And we are showing later that indeed we can compute this term. Now, the use of the triangle inequalities is over. Now we are going to use the comparison lemma to further bound this. And we introduce a new quantity that we called R over bar, index I. This is going to be our threshold. And we write it, we define it in a way that it is a solution to the same equation that we have here, where we replace R with the threshold plus delta over bar I. And this is going to be bigger or equal than exactly what we wanted to bound. So this is our threshold. So is this magic? Is this a way of solving a problem assuming that we already solved it? Well, not really. So the comparison lemma actually tells you that you can bound the solution to a difference equation by the solution of another difference equation where each term individually is an upper bound to the terms of the original equation. So indeed, if you look at the equation for the threshold, it is this same equation, but each term that we have here is at least as big or equal to the term that you have in this equation. So delta over bar is equal to delta over bar, so that's the same. But R over bar is bigger than the absolute value of R. And now you can see, okay, but then it is like saying we already solved the problem, assuming we solved the problem. But indeed, here you can say, okay, but there is some circularity. So the way to show how this works is to start at time 0. So at time 0, we define an R over bar that, by assumption, at time 0 is bigger than the absolute value of R at time 0. How we can do that? Well, by assumption, we know that the state, the input, the output are bounded, the uncertainty are bounded, so it is possible analytically to compute what is going to be the biggest possible value of R at start. And we use that as our initial value for R over bar. So if we can do that at time 0, then by induction, you prove that you can do it for every possible step coming after that. Because indeed, at step 1, you see that at step 1, what you have is this term that we said is bigger than this term, plus this term, they are equal. So the solution at time instant 1 is bigger than the solution of the original equation at time 1. If we repeat this at time 2, we get the same. So we start with something here that is bigger. We add the same thing at both equations. The solution of this one at time 2 is bigger than the solution of the original equation at time 2, and so on, and so on, and so on. So basically, the comparison lemma tells you that if your initial conditions are bigger than the initial condition here, and your input is the same, then the solution of this one is bigger than the solution of the original equation. And this is our threshold. By definition, it is a threshold that is always bigger than the residual in nominal conditions. And this is wonderful because it means, by definition, we get 0 false alarms. The price to pay is that we need to know this bound on delta, and we need to know a bound on the initial value of the residual, which possibly are going to be conservative. So that's the same drawback of limit checking approaches. We always have this kind of compromise. So the key assumption in defining the threshold R over bar as a solution of that equation is that we know a deterministic bound on the absolute value of each component of the total uncertainty delta. And I told you, okay, trust me, we can compute it. Okay, now I will show how we can compute it. So we define it like this. Delta over bar component I at time k is equal to, by definition, the maximum over all possible value of eta and the maximum over all possible value of psi of the absolute value of delta component I at time instant k. So this is not telling so much because basically I'm just telling that the bound is the bound. But anyway, this is the way to compute it. This expression is something that we were able to write previously here. So delta is this expression. And this expression depends on quantity that we know, y, functions that we know, f, and quantities that we can bound, eta and psi. So if we take this expression and we compute it for all possible eta and psi, then we take the maximum and we have our bound. The only issue is that if the shape of f, the nominal function, is nonlinear, then we need to look for a numerical solution to this problem. Instead, if f is linear, then we can find a closed form analytical solution. But anyway, the important thing is that here the max is carried over all the values of eta and psi such that eta I in absolute value is not bigger than its own bound, and the same for psi. So when computing the maximum, we need to provide bounds over which these can vary. Otherwise, we risk not to have a solution. But by assumption, we say we know the bounds on the certainty. So if we know these ranges, then we take all the possible values there, we compute these, we take the maximum, this is our bound. So easy in the linear case, if f is a linear function, not so easy, you need a numerical scheme if f is in general nonlinear. And now let us provide an example. So let us consider a simple dynamical system, spring mass system that is hanging from the ceiling. So we have the spring and the mass m, and the spring is characterized by some elastic constant gamma. So I don't want to use k because that we are using for the time instant. And the length of the spring, the elongated length, is x. Let us assume that the nominal dynamics is this one. So x double dot is equal to minus 1 over m that multiplies the gamma constant times the elongation. But then here we have also some friction. No, sorry, but here we have also some second order behavior. So this is a nonlinear spring. So we call gamma prime the coefficient multiplying the square of the elongation. So the two parameters characterizing the spring are gamma and gamma prime. So this is the nominal. So what are these sources of uncertainty? Well, first one, the true parameters. So the true gamma, gamma prime, and m. We use the tilde now to define the true ones, are different in general than the nominal. So we have parametric uncertainty. Then another possibility is we have some additional force that is occurring on the mass. So we also have some external unknown force that we call Fw, like wind. So let us assume that there is some wind forces occurring here as well. And then we can have some unmodeled higher dynamics that depends on the third power of x, and we call it gamma second that multiplies x to the third power. So the true dynamics is a bit different than the nominal, because we have x double dot is equal now to minus 1 over m that multiplies gamma tilde x plus gamma tilde prime x squared plus gamma tilde second x power 3 minus this force, this extra force. So this is the entire true dynamics. So I have minus Fw because I have a minus here in front. Okay, at this point, we can compute the uncertainty eta simply by taking the difference. So it's just a bit tedious to write all the terms, but the reality is that we just take this one minus this one. So minus 1 over m that multiplies gamma x plus gamma prime x squared minus, then that is plus 1 over m tilde. It was m tilde here as well. That multiplies gamma tilde x plus gamma tilde prime x squared plus gamma tilde second x cube minus Fw. Okay, so this is the uncertainty. So if you want, you can try to further simplify this expression and combine it. And we can do that, and actually we group the terms together by the power of x they are multiplying. So what we get here is, so I already done this computation. So it is 1 over, we get m tilde m that multiplies minus m gamma tilde minus m gamma, we bracket everything, and that multiplies x. So this is the everything multiplying the first power of x, minus, then we have other terms, m gamma tilde prime minus, sorry, I had an m tilde here, minus m tilde gamma prime that multiplies x square, and then similarly now we have minus m gamma tilde second that multiplies x power 3, and then we have the term, oh, probably I just computed the other way around, sorry. That was going to be, yeah, that was going to be a plus here and a minus here, sorry, because eta is defined the other way around. So finally we have a plus f of w. Okay, sorry. So now you see an expression that is grouped according to powers of x. So you see that the uncertainty is depending not just on the uncertain parameters, but also on the trajectory of the system. So if for some reason we have zero elongation, then the uncertainty here is zero, apart from the force of the wind. But if we exclude the force of the wind, when x is zero, the uncertainty is zero. Instead, when the oscillations are big, when we are at a peak value of x, then the uncertainty is at its maximum as well. So the uncertainty is time varying, which means that when we use these to compute the total uncertainty delta, and then we want to compute the bound delta over bar on that, this is time varying. So every single time step, we need to solve this. We need to compute this maximum. So potentially, this is quite complex from a computational point of view. So you may want, in practice, to pre-compute this offline for several values of the state and then interpolate in between, for instance. Because if you want just to apply that, as we have seen, you have a lot of computation to do every time step. Okay, so when we introduce this threshold, we have just seen that it is quite complex from a computational point of view. So is it worth it? Well, yes, it is, because by definition, this threshold is robust against uncertainties, and it is going to lead to zero false alarm rates, zero. And to understand that, we can look at the thing graphically. So the equation for updating the residual can be represented graphically in this way. So you start from a given value of r at a time k, and then you propagate forward this equation. And you have in this equation the residual and the total uncertainty. So if we take all the possible values of the total uncertainty, we represent that via a set capital delta. We know this is bounded by assumption. If we compute all the possible next values of the residual, we get another set, because we have a point and a set going through this equation. the result is another set. But the way we are computing the threshold is such that this set is going to be bounded. And in particular, it is bounded by a rectangle. Why a rectangle? Because we are bounding components individually. So we are bounding, in this example, in 2 dimensions, we are bounding the horizontal and the vertical component of R separately. So if you remember what we have seen in one of the previous lecture, this amounts to getting a rectangle. But this rectangle, by construction, is containing these. Maybe not exactly, could be an over-conservative, but it is containing that. So there is no way that in healthy condition we have a false alarm, because all the residual end here. To get a false alarm, you would need a residual value here outside, but it is simply not possible by construction. So that's very good, a very good property. But you know that if you get 0 false alarm rate, you are getting a non-zero miss detection rate. So now the question is, which kind of detection rate we are getting? To do that, we need to compute again the residual dynamics, but this time assuming that we have a fault. So under a fault, the residual dynamics are different because now we have an additional term, the term representing the fault. So if you just take the dynamics of the system in faulty condition, you do all the math that we have done before, then you get to this. It's no big surprise you get this additional term. So this additional term now is making the residual bigger than in the case where we hadn't, of course. Well, bigger, well, assuming that the sign of I is the same as the sign of delta. If the signs are different and opposite, they are canceling out. And so you already see what is the potential issue leading to missed detections. But in case you have no cancellation, so if the sign of phi is the same as delta, then the effect of phi is like to have an extra vector pointing somewhere. And then we can get out of this set. It depends. So if we were here, probably we get out. But if we are here and phi is pointing this way, we don't get out. So there is another reason why we can have no detection. But if we are in a situation like that, phi is taking out of the threshold set. So can we characterize in which conditions we have that nice behavior, phi that is taking us out of the threshold set, and when we don't have it? Well, what we can do is to take the solution for the residual and for the threshold and compare them. So now in faulty condition, the residual solution is this one. And now we wrote that in full. So this is a convolution sum. So this is no longer a difference equation. This is a solution. And similarly, this is the solution for the threshold. We need now to compare the two. And we need to see under which condition phi, that is here, is such that this one, in absolute value, is crossing this one on a component by component basis. Well, if we do that, and there is some mathematics behind that, we can get to this result, this theorem about detectability, which says if there exist 2 time indexes, k2 bigger than k1, that is as big as k0 or more, such that the fault function phi is fulfilling these following inequality for at least one component I, then we have detection at time k2. And what is this inequality telling us? We have something on the left side that depends on the fault function, and something on the right side that depends on the threshold. And we have here a 2 in front of that. So very intuitively, this is telling you if the fold function is so big that its influence is at least 2 times the residual, 2 times the threshold, then you're going to cross the threshold. So before we look into that more, I want to show this on a very, very intuitive basis. So we said that both the uncertainty and the fold are occurring in the dynamics of the residual now, and they are summed together. So on a very intuitive basis, we want to see when these two things are crossing the threshold. And so, if they have the same sign, they are combining together, the result is bigger, and then we probably cross the threshold. But if they have different sign, then they are canceling out. So the intuitive idea is that if this one is at least twice what you have on the right, you can cross it. Why? Well, because let us think the worst case first. In the worst case, this is causing the maximum possible uncertainty on the negative side, and this is positive. So in the maximum possible, so in the worst case, what we have here is minus delta over bar. So let me allow it to be non-rigorous. So delta over bar is not going to cause anything bigger than the threshold itself, because by construction the threshold we built that way. So let us replace it here by R over bar. So we have in the worst case R over bar, and then we have phi here. This should be bigger than R over bar. So in this case, you see that if the effect of the fold is at least twice the threshold, then we are crossing it, because we have minus the threshold plus 2 times the threshold is equal to the threshold. And then if you have just a little bit more, you cross what you have on the right. So now this is non-rigorous because we have our observer in the middle. So we don't directly compare these and these to the threshold because there is the dynamics of the residual in the middle. But if you are rigorous and you compute the solutions, then you get anyway to a similar situation. But in place of these and these, you have terms like this. So indeed, if you look here, we have a sort of convolution sum of the effect of the fold. So this is the effect of the fold going through our observer, basically. So the effect of the fold going through the observer must be at least twice the threshold. And then it makes more sense, because now this is rigorous. So here it was not really rigorous. We just said, okay, we have effects, but we didn't write them full. So this is written in full. So if you want to prove that, you can do it. It's not difficult. You need by writing the residual and threshold solution at starting time k1, and then you are using the reverse triangular inequality. Use the assumption that there is yet no detection at k1, and then you impose detection at k2. So if you impose detection at k2, then you simplify a lot of terms. You can do some upper bounds using the reverse triangular inequality, but you get to here. And this thing is saying to you, okay, apart from the effect of the filtering of the observer, the fold should be bigger than twice the threshold, which is an indirect way of saying that the fold should be bigger than the uncertainty, twice the uncertainty. And this makes sense indeed. Because in order to detect something with a threshold that is built on the maximum value of the uncertainty, the fault should be bigger than this. And should be bigger than this, and also consider the very unlucky case where the fault and the uncertainty have opposite sign. And this is a mathematical way of describing where is the compromise in this approach, where the misdetection rate is going to be bad because of the fact that we wanted a zero false alarm rate. So the compromise is here. We are bounding, constraining our detection capabilities on the size of the uncertainty. So if you have a system with a lot of uncertainty and you have small faults, you're not going to detect them. Never. And this is the really bad downside of this approach. At least it is the downside when you are using deterministic thresholds like these ones. But of course, at this point, you can imagine that if we have different kinds of thresholds, maybe we can relax this and get some way better detection. And indeed, as we have shown in the lecture on the change detection algorithms, the idea is to use probabilistic thresholds. So if you have probabilistic thresholds, you are trading in some false alarm rates for better detection rates. And indeed, this is something that we can do. So in order to introduce probabilistic thresholds, we need to go back to our equations. Now we can even write them in some more general case. So we assume that the dynamical function is some complex function of the state, the input, the uncertainty, and the fault itself. So this is making it very general. So now we are no longer assuming that we need to write the effect of the uncertainty and the fault as an additive function. But anyway, this is just a way of writing it down because it's completely equivalent, as we said. But now these uncertainties, they are treated as random variables, and we don't assume that they have a bound. Because, well, as we said in other lectures, usually there are no bounds. So if you have a Gaussian variable, there are no bounds. You have a mean, you have a variance, but you don't have a bound. Still, we need to have some assumptions. And this f should be a nice function, and even if the uncertainty is unbounded, f is not going to be unbounded. But this is just some working assumption. So at this point, we proceed pretty much the same way that we proceeded before. So we build our observer. Our observer is assuming that the uncertainty and the fault are 0 here. We get our residual, and the residual dynamics is going to be the same. It's just written some way different because we have now a different formulation for f, but the idea is exactly the same. So residual is a filtered version of the total uncertainty, with the filter gain being the matrix lambda, the gain of the observer. Now, anyway, R is going to be a random variable because it depends on delta, which is a random variable, and delta is a random variable on the same probability spaces as eta and psi. So how can now we bound R now that R is a random variable? Well, actually, we already know how to do that, because this is what we did in the lecture about change detection algorithms when we introduced the probabilistic approaches. So on R, we can run any of the tests that we have seen. So T student, F, chi-square, and so on. The only thing is that usually R is a vector, so we would need to apply one of the tests that works for multivariate variables. And basically, we presented one such test, that is the test based on the Mahalanobis distance. And this is what we can do. And now, the thing is that as we introduced previously that graphic representation, now you can see what does it mean to apply the Mahalanobis distance test to this case. Because we have R. So let us assume we are starting at time k. We measure r, so it is the estimation error of our observer. So at time k, r of k is a deterministic variable. We just measured that. But the next value at r k plus 1 is going to be a random variable, because it's going to be r and delta through this mapping. Delta is a random variable, so the result is a random variable. So we can some way express the set of all the possible delta again as this capital delta here. And so when it is going through this mapping, you get another set here for all the possible residuals at time k plus 1. But the thing is that if this is a random variable, this set here is unbounded, possibly. But we said our function f is nice, everything is nice, so in the end we get some set here on the right side. And having a threshold based on the Mahalanobis distance, as you can guess, is like trying to approximate this with an ellipse. Because we have seen in the lecture on change detection algorithm, so when you define a threshold on the Mahalanobis distance, it's like defining boundaries on your variable that has the shape of an ellipse. And the boundary of the ellipse have constant Mahalanobis distance. So the idea is that once you finally compute the next residual, you compute the Mahalanobis distance of that, and then you compare it to a bound, to a threshold d over bar m, that is computed, as we said, using the Chebyshev inequality. So we define it as n number of dimensions of r over alpha, such that this inequality is holding. So the probability of having a false alarm is less than alpha. So alpha is something that you can tune to your likings. An important thing, so as in all tests, the parameters of the test are based on nominal healthy behavior. So you need to be able to characterize what is the mean and covariance on the residual in healthy conditions. You do it somewhere, some way, once, you keep the result, and then you apply them to the actual samples of R. So these mu and c, they are not continuously updated, because otherwise, when you have a fault, mu and c are going to be poisoned by the fault, and the test will never fail. So you need to have mu and c fixed to values that describe the behavior, the statistical behavior of R in healthy conditions. And then you can build a test such that you are detecting faulty behavior. Okay, so let us introduce an example. So the example is a classic one. It is based on the 3 tanks system. It is a benchmark that is used a lot for fault detection. You have tanks 1 and 2 and 3. 3 is in the middle. You have pumps directly feeding tank 1 and 2. You have pipes interconnecting 1 and 3, 2 and 3. And finally, you have a drain out of tank 2. In discrete time, you can write the dynamical equations of the tanks, and you get a square root here of 2 times g, so this gravity acceleration that multiplies differences in levels. So if you apply simple conservation of energy, you get equations like that, where you see that the flow through the pipes depends on the square root of the difference between the levels in the tanks. So of course, the water is flowing from the tank that has the higher level to the tank with the lower level, and this is captured by the sign that you have here. In these equations, you have Ts, that is the sampling time. So this is to implement basically a discrete time integrator. you divide by the section, the cross-section of the tank, and then other parameters that you have here are, yes, these are the cross-sections of the pipes. So A1 cross-section of tank 1, A1P cross-section of pipe 1. This is pipe 1, this is pipe 2, and this is pipe 3. Okay, so once you have these equations, you can introduce uncertainties, and we are considering parametric uncertainties. So we know what is the nominal value of tank and pipes cross-sections and outflow coefficients of the pipes, but the actual parameters are off by 10, 15, and 5%. And then we model a leak in tank 3 at some time with some constant b and some size that it is not written here. Okay, so I can't recall what is the size, and for some reason this dropped from the slides, but I will find out and post it. Okay, what's going to happen? So if you implement the observer that we just introduced today, so the fault detection observer, you are going to see a plot like this one. So you have the threshold that pretty much is constant, and the residual is doing this. So before the fault, it is influenced by measurement noise and uncertainties. But when you have the leak, you have initially a peak. And in this case, the leak was big enough for the peak value of the residual to cross the threshold. And indeed, we have detection at this time. But then something is happening. So the fault is still present, so you would assume the residual to be big. But instead, what's happening is the residual is going back pretty much to values like it had before the fault. A bit bigger, but not so much bigger. And you may wonder why. Well, the issue is all in the observer. So as we said, the observer is tracking the system, is compensating for uncertainties. And when you have a fault, the observer is compensating as well for the fault. So after you have the fault, the output feedback error injection term in the observer is trying to compensate that and bringing the estimation and bringing the estimate of the observer back to the measurement. And so the residual is going back to 0. So the only way to detect a fault is for the fault to be big enough and fast enough to initially take the system far away from the estimate of the observer, at least for some time. And during that time, you have a detection. Then, if the fault stays pretty much constant, the observer will start tracking also the faulty behavior. So this is quite a downside of the approach. So basically, the fault, if it is slow, will not be detected, will be filtered out by the observer. But if the fault is fast enough, it will go through. And this is captured by the detectability theorem, actually. So here you have the filtered version of the fault. You need that to be able to cross the threshold. So the filter, so the observer again has an importance here. It is affecting the fact that this is going to be able to cross this or not. And so basically here we have yet another take on the compromise between robustness and detectability. So we have an observer that is filtering out measurement uncertainty, and so indirectly it is making us, and indirectly it is making the threshold smaller because it is already filtering out noise some way. But you also risk to filter out the effect of the fault. So you need to find a compromise between filtering the noise and being sensitive to faults. Anyway, in this case, we implemented a deterministic threshold, not a probabilistic one. Okay, so today we finished our introduction of fault detection observers. We characterized detectability. We introduced a deterministic and a probabilistic threshold. And the next series of lectures, we are covering the next step, which is fault isolation and estimation and fault learning. And that will complete the fault diagnosis.